All right. So let me pull up my PowerPoint. This is the last lecture of the semester. Sorry, I had to cancel class, guys. It was a little bit crazy. But this gives you a chance to have this lecture earlier than expected. So you have a little bit extra time with this because I will see you for lab on Monday. So let's start here. I'm going to do the same thing I did before. I'm going to have my notes page up a little bit higher so I can see, and you can kind of take notes with me. I'll post these notes pages on eLearning as well as the video, and then you can come to class on Monday with questions from all the material. So I am in my home this time, so there's not as much noise, hopefully, in the background. You may hear doggos in the back, but other than that, should be good. So what limits brief high-intensity exercise? We talked about this in the last lecture with regard to cardiovascular exercise, but now we're talking about anaerobic performance. So what limits brief high-intensity exercise lasting just a few minutes? Remember those systems that we talked about, the ATP PCR system, anaerobic glycolysis, and then aerobic glycolysis. So really your limiting factor here in what limits something like 1 RM is a 1 repetition maximum. It's the most amount of weight you can lift one time, 1 repetition maximum. If you can't lift the weight, then it's beyond your 1 repetition maximum. And if you can lift it more than once, then it's not your 1 rep max. This is the best measurement we have of muscle strength. We'll define what muscle strength is next, or coming up here. So really what limits this performance? Like a 1 repetition maximum, excuse me, or something like a 3 to 4 second exercise, like a typical football play on average lasts about 4 to 6 seconds. So that what limits brief high intensity exercise would be our ATP PCR system that's being used, but also just the ability of muscles to recruit motor units. So the generation of maximal force, we said before, a bigger muscle, a stronger muscle, and more fast twitch motor units that are larger equals more force production. So your limiting factor here is just your muscle's ability to generate force. Now, in the few seconds of exercise, ATP is offered in ample amounts. You don't have to worry about running out of ATP. So in that first few seconds of exercise, you've got plenty of ATP. So something else has to be a limiting factor, and that happens to be intramuscular, how well the muscle is able to generate force, or how much it's able to generate. Lasting 10 to 30 seconds, now we run into more energy system depletion. So your ATP PCR system is your predominant energy source of ATP in the first 10 to 30 seconds of exercise. Once you get beyond 30 seconds of exercise, anaerobic glycolysis has now begun producing more ATP and can continue to supply ATP. But in that first 30 seconds of exercise, and it takes about 30 seconds to deplete all of your PCR stores, and the only way to replete them is to rest, if you don't recall from the previous lecture. So here, anything lasting up to 30 seconds, say a 100 to 200 meter sprint or a 50 meter swim, your major limiting factor is PCR depletion. So really when it comes to weightlifting and strength training, your big limiting factors are how much force can the muscle generate, and then how sufficient or how efficient is your ATP PCR system. So think things like creatine supplementation is big, because basically what creatine does is just provides your body more creatine than it can produce from the liver. So supplementation basically just gives you more creatine, which means you can create more phosphocreatine, which means you can donate more phosphate to ADP to produce ATP. So creatine supplementation just basically saturates the muscle with that kind of energy, that phosphate donating molecule. So before we move forward, we're going to define 3 things with regard to strength training: muscle strength, power, and endurance, because they are very different, but all kind of can be grouped into the world of muscle and strength training. So Muscle strength is the most amount of force that a muscle can produce in a single movement. So I say here, how do we measure muscle strength? I said before, 1 repetition maximum, 1 RM. And it completely depends on size and cross-sectional area because, whoops, again, a bigger muscle is a stronger muscle. So muscle fiber type plays a huge role. Fast twitch muscle fibers are larger than slow twitch. We talked about fast twitch versus slow twitch back in the first exam unit. So go back and review that if you're not kind of recalling the differences between fast twitch and slow twitch. And lifting weights at or greater than 70% of this 1 repetition maximum actually is the first point at which fast twitch B fibers are recruited. So we've got 3 types of fibers: slow twitch fibers, fast twitch A, and that's annoying, and fast twitch B fibers. They recruit from slow twitch, then fast twitch A, and then fast twitch B. So they recruit in that manner. Recruitment occurs in that order. The other thing that's important to note is that neural factors are contributing to muscle strength in that, think about motor unit recruitment. In a healthy individual, typically motor unit recruitment is asynchronous. So let's go in untrained. Motor unit recruitment is asynchronous, meaning motor units do not all recruit at once. With training, that changes. So as motor unit recruitment synchronizes and more motor units are recruited, force production is able to increase. So we'll talk a little bit about that when we get to adaptations. So muscle strength can increase by tons over just several months, but it completely depends on where you start. So it says 20 to 100%. Now think if somebody is already very strong, they don't have as much to gain, but someone who is relatively weak has a lot farther to go. So in this principle of specificity, we will talk about as we keep moving. Another definition is muscle power. Muscle power is basically force production, but takes into account time. So how fast are you lifting a weight? It's your ability to generate force rapidly. So when you think power, think explosiveness. So the definition here is power is equal to force times distance over time. And force times distance is work. Distance over time is velocity. So any one of these equations can help us calculate power. Now, I usually use force times distance over time, force times distance over time, because that's the easiest way to think about it. The force is weight lifted or tension on the muscle. Distance is how far move it. And time is how fast. So all of that said, power in general, think of like powerlifting, something like a hang clean. So if you lift a weight, say 100 pounds, in 2 seconds, and then you lift that same weight in 1 second, power output increases when you lift that weight in less time. Typically, the type of training that improves power is Olympic lifting. Like hang cleans, power cleans. So if you don't know what those exercises are, you can Google hang clean or power clean or Olympic lifting, and tons of videos will pop up on that. Muscle endurance is the last definition we need to talk about. That's the ability to maintain force over repeated contractions or over time. So you can high repetitions, lot of volume, lower weight, and that improves muscle. And by improving strength, you're also improving muscle endurance. So it's your ability to maintain force, over time, or repeated contractions over time. So for example, let's go down here. If two people are lifting a weight, say 200 pounds, is in a squat. Person one lifts that weight 10 times, and that's as much as they can do. Person two lifts that weight 20 times. That means person two has greater muscle endurance. So all that being said, keep those definitions in mind as we continue forward. Now let's review the types of contractions, and I'm going to do this quickly because we've done this before. So isometric contractions. Iso means same, metric means length, so the muscle is staying the same length but producing force. So when the joint, these types of exercises are typically used when joint mobility is limited, and that can help stabilize the joint. So you're still actively working the muscle, but not necessarily moving the joint. So if there's a joint injury, it may be a good idea to use an isometric exercise. Isokinetic exercises is the same speed. So these exercises are performed at a constant speed. This is usually, so the Cybex machine, this is a Cybex machine, is able to control the speed at which an activity, a lift, is being performed, so that your muscle has to generate force against that kind of lever or this arm here. And you can measure changes in muscle force production while keeping speed constant. So this is usually, it's used in rehab settings, but it's also, it's not sports specific, but it also is used in research settings. Okay, stop yawning. All right, let's keep moving before I fall asleep. Isotonic contractions we've talked about before. Iso is same tone, right? So same, the force here is the same, or the load is the same. So the muscle length changes while generating force against a movable resistance. So the resistance, or this load, is fixed, like a barbell or a fixed weight. So this is the most sport specific and most applicable to sport specific training, but can also provide a risk of injury just because of how highly mobile these exercises are, and how they're not as controlled as isometric and isokinetic exercises. We've talked about concentric contractions versus eccentric contractions. Both are isotonic, but concentric contractions include shortening of the muscle, and I kind of explained that as when the 2 points of attachment are coming closer together. So concentric equals shortening equals points of attachment of muscle move closer together, which means eccentric is lengthening, points of attachment of muscle move apart. So like the down in a squat is an eccentric contraction of the quads, whereas the up in the squat is a concentric contraction, both of the quads, so that the quadriceps muscles are still doing the job there. They're still contracting, but in one phase they're lengthening, eccentric, in one phase they're shortening. So down of a squat equals eccentric contraction of quadriceps. Up equals concentric. Now the role of eccentric actions, if you've heard somebody say they did negatives in the gym, or they were going to the gym to do a negative day, or negatives, that negatives is eccentric contraction. So it's just kind of the lay term for eccentric focused muscle contractions. Now maximum gains occur in strength because when you do both concentric and eccentric muscle actions, but you can actually lift more weight. You can actually contract the muscle more forcefully in an eccentric contraction. So more force produced by eccentric contractions. And if more force produced, then more intramuscular damage occurs in response to training. And that means more growth. And more growth is hypertrophy. And a bigger muscle is a stronger muscle. So those maximum gains are typically seen in eccentric contractions, and that's mostly related to these 2 points here. When you're performing an eccentric contraction, rates of cross-bridge detachment are less than in a concentric contraction. And basically what's happening is titin, that molecule that anchors myosin to the M line, tightens, and that helps increase, facilitate muscle contraction. Now, that's as far as we're going to go with regard to how eccentric contractions contribute to a greater force production compared to concentric, but there's a link here with a comprehensive overview. It gets complicated, so I'm not going to go into too much detail. That's about as much as we're going to do. But because you can lift more weight, you can generate more force in an eccentric contraction, you induce more injury to the muscle fibers. And is that good or bad? It's good, mostly because that increase in intramuscular damage in response to training stimulates more growth. And growth, or hypertrophy, means more built to generate more force. Remember, once upon a time we talked about the internal components of muscle, like sarcomeres of actin and myosin, and sarcomeres line up into myofibrils, and myofibrils pack into muscle cells. So as hypertrophy occurs, protein synthesis in response to this training synthesizes all of the components of sarcomeres and just smashes more sarcomeres into each cell, causing hypertrophy. So let's talk about what happens in adaptation to strength training, because we've defined now, we've discussed what limits strength training exercise, think ATP PCR system if it lasts a little bit longer, or your muscle's ability to generate force. Over time, that changes with training. You have to overload the muscle, think isotonic contractions, a combination of concentric and eccentric, can potentially focus on eccentric contractions to generate more force in the muscle and create more damage. There's a note on here that says it causes muscle soreness. DOMS is delayed onset muscle soreness. We'll talk about that later, so we'll come back to it. Now, these neural adaptations that occur in response to strength training. So I think we talked last time about cardiovascular adaptations. So what happens with the heart? What happens with the size of the heart and the chamber and the outer ventricular wall? What happens in response to cardiovascular exercise to the cardiovascular system, but also the respiratory system. And then we did the respiratory lab last week, or 2 weeks ago. I didn't see you last week. So now we're focusing on just neuromuscular strength training adaptations. And basically in the first 6 to 8 weeks, this can also go up to 10 weeks. The predominant increase in strength completely comes from neural adaptations. So this is before hypertrophy occurs. So make note of that. Like, hypertrophy is not happening here yet. So an increase in muscle size is not occurring. So the increase, but strength is improving. So strength increases without an increase in muscle size, without hypertrophy, due to neural adaptations. Now, these neural adaptations are listed here. Synchronization of motor unit recruitment, which is, I'm going to say MUR, motor unit recruitment, is asynchronous in untrained individuals and becomes synchronous with training. Now, if you are synchronizing and increasing the number of motor units activated to generate force, that means you can generate more force. And the same weight in untrained state feels easier to lift, which is basically one of the major reasons why in the first 8 to 10 weeks of exercise of strength training, you're lifting weights, but if you keep lifting the same weights, that eventually gets easier. So all those neural adaptations are just saying, let's synchronize motor units, make this weight easier to lift. We're basically just becoming more efficient in the muscle. Now, a couple other things facilitate that, like reduced inhibition of motor units. You have an inhibition of motor units is protective in the muscle to prevent too much force production. I don't like the way that sounds, but I'm going to write it anyway. Too much force production, which prevents potentially injury. But with training, this inhibition is inhibited to allow greater force production within, I'm going to say within limits, within, I don't know, to a certain extent, because the muscle retains this protective nature, this protective effect, this protective mechanism. It just quiets it a little bit. So that being said, a couple other things happened. We talked about co-activation. So remember, go back and define what co-activation in skeletal muscle. What is it? So go back to your first exam unit and take a look at what we did a lab in which co-activation was a focus. So we were talking about activation of the agonist and antagonist muscles. So again, if you don't remember what an agonist or an antagonist is, also go back to exam unit 1 and go review those terms. So remember isometric, isokinetic, isotonic, concentric, eccentric contractions, agonist, antagonist muscles, synergist muscles. All of those terms you should be familiar with and remember from exam unit 1. And if you don't, go back and review them. So I'm going to use those terms by reducing activation, which is co-activation of the antagonist muscle. This facilitates activation and force production in the agonist muscle. And lastly, plus increased activation of synergist muscle also improves force production in the agonist by just helping that muscle do its job. So overall, force production can increase around that joint because of all of these neural adaptations, and they are what's happening in the first 6 to 10 weeks of exercise, where no hypertrophy is occurring yet. Basically, what you're doing is just producing intracellularly the machinery for hypertrophy to occur, but that takes time. So while that's taking time, neural adaptations are occurring to help you improve strength during that waiting period. Did I jump too quick? That's neural adaptation, metabolic adaptation. So we talked quite a bit about metabolic adaptations in cardiorespiratory exercise. But basically, look at your system that you're using. This is glycolysis. You're converting pyruvate to lactate in carbonic anhydrase, and the carbonic acid equation is basically bicarbonate is buffering that that acidity as it's being produced. So basically, a couple of things happen. Increase in muscle glycogen stores. What that does is, if you have more glycogen, you have more glucose. And the only source, more glucose, and the only fuel source for anaerobic glycolysis is glucose. So if you have more glucose, if you have more glycogen, then you've got more glucose available. If you have more glucose, you can produce more pyruvate, convert to lactate, and ultimately you're producing ATP. So increasing muscle glycogen stores, increases in anaerobic enzyme activity that drive anaerobic glycolysis. So like the enzymes kind of listed here, there's a couple of them. Lactate dehydrogenase is a big one in anaerobic glycolysis, which is why we have a box around it. But also increase your buffering capacity. So your body is able to produce more bicarbonate. Your kidney is pretty heavily involved in buffering hydrogen ions. They can excrete and HCO3. Bicarbonate can be produced in the kidney. So pretty big deal, which is another way that your body is able to handle the changes or the production of acidic compounds like lactate and buffer them to prevent buffering capacity and fatigue prevention. Big deal. And also you just decrease your intracellular disturbances of things like calcium and potassium. So your kind of nervous system gets better at monitoring and generating and reestablishing resting membrane potential once action potentials occur, and the circuit pump is better at pumping calcium back into the SR. So a couple of those metabolic changes can really make a big difference. And there's also always a table that I have popped in here. I'm going to turn this on for a quick second and not take notes from the current slide so we can see what's underneath it. So basically these structural adaptations, we talked about neural adaptations, metabolic adaptations, and now structural adaptations. The biggest being in sprint and strength training, muscle, that's FT is fast twitch muscle hypertrophy. And what does that do? And I said, hint, think cross bridges. So this video, if it wants to work on my laptop, is showing you cross bridge formation. That's awful. I think it looks like it's almost going backwards. I don't like that at all. If I get a chance to on Monday, I will show this to you in class because that video is just sketchy at best. It's a good video and it shows you cross bridge formation and detachment. But basically the point of this is to say with hypertrophy, you pack more sarcomeres. Basically, the process behind that is related to cells. Let me see where I'm at here. Hypertrophy. Yeah, we'll talk a little bit about on this slide. So I'm going to stay here. So basically, this hypertrophy. Yeah. Is stimulated by strength training due to intramuscular damage, which means sarcomeres are basically broken down, and that provides a signal to cells. This happens after the first 6 to 8. I also will put in here the same caveat up to after 10 weeks of strength training. Gains are mostly due to increase in size, hypertrophy of the muscle, and the amount of connective tissue between the fibers, which helps prevent injury. So basically, as muscle cells get larger, the connection of muscle to bone gets stronger as well. So along with hypertrophy, you get stronger tendons as well, help support the stronger muscle. So as these sarcomeres are broken down, That's a signal to cells called myosatellite cells. These are cells that we, I think, talked about back in that first exam unit when skeletal muscle equals accessory cells in skeletal muscle that aid in repair of damaged myocytes. So basically what they do is these cells were once upon a time myoblasts with single nucleus. Those myoblast cells during development fuse their membranes and contribute to a multi-nucleated myocyte. Those myoblasts that don't become a myocyte remain myosatellite cells in muscle. And then when muscle is damaged, needs repaired, or it needs to be, if hypertrophy is stimulated, those myosatellite cells can contribute their nucleus again. They basically just, in the damaged muscle cell, fuse their membrane at the damaged site of damage and contribute the nucleus and the intracellular machinery to produce more sarcomeres. So really important. Basically, that increase in protein synthesis exceeds degradation, and that just results in a net gain in muscle protein. And muscle protein is actin, myosin, and all components sarcomere. So basically what you're doing in response to hypertrophy is just packing more sarcomeres into muscle cells. They increase in size, and again, bigger muscle is a stronger muscle. Now, if you want to gain muscle size as a whole body, you need to exercise the entire body. So this principle of specificity basically just says your body will respond to the type of training you're doing. So if you only lift upper body, then your upper body will hypertrophy. Think, skip leg day. I know you've seen this guy walking around the gym with little teeny tiny legs and big huge arms. But basically, in saying that human is a walking, talking case study on specificity. So low intensity strength training recruits slow twitch and fast twitch A fibers. So those fibers will adapt. All of the things that we were talking about: neural adaptations, metabolic adaptations, and hypertrophy. You have to increase intensity beyond 70%. I'm going to say of 1 rep max to improve and stimulate hypertrophy in all muscle fiber types, because that recruits slow twitch and fast twitch A and fast twitch B. You cannot, muscle does not, I'm going to put that there because there's a caveat to it. We're not going to talk about it. Does not recruit ever only fast twitch B. Order of recruitment is always, and I'm going to do that again because there's exceptions to the rule, but we're not going to get into them. Always slow twitch, then fast twitch A with greater force. I hate that. Then fast twitch B. And maximum hypertrophy occurs when fast twitch B fibers are recruited, because you're getting hypertrophy and greater than 70%, 1 repetition maximum intensity will hypertrophy all fiber types, because all fiber types are recruited. You have to recruit slow twitch first, then you recruit fast twitch A, and then you recruit fast twitch B. It's all a feedback mechanism. There's receptors in the muscle that sense stretch, and as the muscle stretches, that a small amount of stretch will stimulate fast twitch muscle fibers in response to contract. Bigger stretch, greater stretch, then fast twitch A. Higher than 70% max of a one repetition maximum is a lot of stretch, and that a lot of stretch stimulates now all fiber types to recruit. So maximum hypertrophy occurs in response to high volume training, and the high volume is lots of repetitions, about 70% of one repetition max. So the intensity is that percentage. The volume is repetitions. So I'll use this word volume a couple times. So volume equals repetitions. Intensity equals percent 1 RM. Now, strength training obviously improves muscle strength. Think specificity. What type of program? So there's a good question here. What type of program would you do with a football team? Now think about what a football team does. Let's talk about that specificity. Do you want a football player to run long distance? Would they ever need that? No. So that, like, why would we need distance training in football players? They need power. They need explosiveness. They need strength. They need to overcome the strength of another individual and the power of another individual. So really, in a football program, focuses on strength and power. Swimming focuses on endurance. So big difference. And depending on the training program, we will modify volume, sets, frequency, days per week, or numbers of exercise or exercise bouts per day, or days per week. And then intensity, which is resistance, or like I said, percent 1 RM. Now, why specificity? So basically what we're doing when we're training is training our metabolic energy systems. Like, look at the difference in these 3 individuals: the gymnast, the football player, the runner. Very different body types. So we're going to train muscle very differently depending on the needs of the sport. Now, muscle responds to the physiological and metabolic demands of that exercise. So if you're running and you're only recruiting slow twitch muscle fibers, those slow twitch muscle fibers will adapt. Fast twitch A can adapt as well and try to become a little bit more like slow twitch. But if you're only recruiting those fibers, they're the ones that are going to adapt most. So basically, training has to reflect the energy demands of the energy systems of your specific sport. Now, a sport like soccer uses all energy systems. So we train all energy systems. And endurance training will only enhance oxidative capacity. Strength training will induce fiber type hypertrophy. So if you're a combination athlete, then we will do both. So we will have soccer players run, we have soccer players sprint, we have them do agility and plyometric exercises. We also have them lift weights. So soccer is a perfect example of an all-encompassing sport where we train for strength, power, and endurance, as well as cardiovascular endurance. So in terms of overload, this principle of overload just means that your muscle needs to experience something beyond normal daily activities to adapt, to be pushed to hypertrophy. So muscle adapts to physiological and metabolic demands of exercise, but if you don't exercise, there's nothing to adapt to. So you have to push yourself. You have to go above and beyond to get to the point where we, quote unquote, overload our muscles. Now, training loads must be progressive. So you don't just start exercising and just go hard and as fast as you can. If you do that, you can get injured. So we always start progressively and over time add weight. And basically what happens is as you perform one training program, your body plateaus. So a plateau happens when the body has adapted to one training program. And you can actually start to use less energy to perform the same amount of work than during the adaptation phase. So how do we avoid this? We avoid plateaus by changing our workout. So basically, this plateau in performance it happens because workouts are not continually adjusted. You have to accommodate to training adaptations or accommodate training adaptations. So overload can be achieved by altering any one of these factors: intensity, duration, frequency, type, or a combination of those. So what we usually do is use something called periodization. And periodization is where we train athletes in a season. That season may be, so seasons equal preseason, season. So I think competition, postseason, which would be playoffs, and off season. These seasons can vary pretty greatly with regard to their total length. Now, athletes, while we're training them, are typically also playing their sport. So we're very careful in gym, in a weight room, with how much, what volume we do and what intensity we're doing. So during each cycle, the training is varied. So intensity and volume are worked together. So they have to work together because they're in intensity and volume are typically inversely related. So as intensity increases, volume decreases, meaning that at a very high intensity, your 1 repetition maximum is the most amount of weight you can lift one time. So it's 100% of your 1 rep max. You should be able to lift that one time. As you decrease that intensity to 90% or 80% or 70% of your 1 repetition maximum, you should be able to lift that percentage more times, which would increase volume. So as intensity decreases from 100% of 1 rep max to 50%, you can lift more and more and more weights. So volume, you can lift more and more and more repetitions, so volume increases. So we just mess around with these kind of intensity and volume relationship. And what happens is we get something called microcycles that last about 1 to 2 weeks. So this microcycle, can you see here, this kind of step increase? Every couple days, we increase weight, or so we increase intensity, or we increase repetition, or volume, or we increase both. So we're increasing intensity and volume in a microcycle, and then we take a break. That break is active recovery. So at that peak of microcycle, we break for typically about 1 week of active recovery. And active recovery means still exercising, but much lower intensity, typically higher in volume. This prevents injury by allowing muscles to recover. But if you stop training altogether, you will lose what you've gained, can lose some of what you've gained. Allow muscles to recover without losing what has been gained. So pretty big deal. Those weeks of active recovery are really important. They're just there they also prevent boredom and just doing the same thing and just always going hard. You can't always go hard. So to prevent that, we do a week of active recovery. We don't decrease all the way back to where we started. We just decrease to somewhere a bit lower than this intensity in this microcycle. So each microcycle, because the next microcycle starts where the active recovery leaves off, you can then gain even further. And then you go down in intensity, maybe change volume a little bit, depending on how low the intensity is, but you don't ever decrease to the previous volume or intensity. So you always go down, but maybe like 2/3 of the way, 3/4 of the way. You don't ever go back to where you started at the beginning of that microcycle. So those transition phases, I'm going to say they're called transition phases on that figure, but I will always refer to them as active recovery phases. They're about a week. Prevents boredom and decreases intensity but not to point of previous microcycle start. And then the next microcycle picks up, begins at intensity of active recovery week. So you can gain even further. And hopefully, by the time we hit this kind of this macro cycle would be like a season. We hit the end of the macro cycle, so called a season. We have athletic peak performance. So yay, we perform well. Usually if we are in season and we're about to transition into post-season, we want to hit this peak. And when we hit this peak and head into postseason, so playoff season, we're in our peak condition and can be the best athlete we can be. So it prevents injury, prevents boredom. It also prevents overtraining. So these active recovery weeks are really important in preventing overtraining. And if somebody overtrains, they tend to get hurt. And if you're hurt, then you can't compete. So ultimately, this periodization is a really important concept in strength training and conditioning, in athletic strength training and conditioning, that does all of these things and helps our athletes peak at a particular time, which would be like something like major competition, so postseason. Really big deal. So there's an example here of prescription for exercise and strength training. Now, to gain max strength, so think increasing 1 repetition maximum, 2 to 6 repetitions. Max strength is just force production, so you shouldn't be able to lift this weight many times. It should just be very high intensity within 3 to 6 sets. To hypertrophy a muscle, this may be something that a lot of you didn't know. To gain size, we really want to lower weight, so a moderate intensity and higher repetitions, 8 to 12. Now that stimulates muscle growth for a number of reasons. Time under tension is a big deal, but moderate weight would be like 60 to 75% of a 1 repetition maximum, and lift that weight 8 to 12 times. So 3 to 6 sets of 8 to 12 repetitions. To gain muscle endurance, obviously muscle endurance is defined as the number of times a weight can be lifted or the amount of tension force that can be produced and held over time. We're going to do tests of muscle strength next week. Moderate weight, so think lower than muscle hypertrophy, so you can produce that tension more time, so increase repetitions. If you're focusing on muscle power, think explosiveness. And you can only be explosive and get the most out of a muscle at a moderate intensity a certain number of times. So if we're focusing on muscle power, we're focusing on explosiveness, but you need a maximal break in between to allow muscle time to recover. Now, this moderate weight may seem weird, but when you're focusing on muscle power, think about how quickly you can lift your 1 repetition maximum. The most amount of weight you can lift one time. Shouldn't be able to lift it very quickly. So you need to lower the weight so you can lift it faster. So when we're focusing on muscle power in our athletes, focusing on power, we lower weight to, say, I don't even know, 40 to 65% of one rep max, and focus and lift the weight as fast as possible. I'm going to go under control with good form. We always focus on form first. If you can't lift a weight with perfect form, shouldn't be lifting it. So that's always our focus first. But for in general, for health-related fitness, it can vary. It depends on what your goals are. So health-related fitness is usually moderate weight, 8 to 20 repetitions. I usually tell people to start with 8 to 10 reps or 6 to 10 repetitions and just perform the lift under a weight that you can do with good control and form, as many times as you can, with a weight that's comfortable for you. So there is no magic number there. But that's pretty good in terms of prescription. And this particular table can help you answer some questions on your lab assignment, for the strength lab assignment. Now let's finish up and talk about delayed onset muscle soreness. and bad things that can happen. This isn't a bad thing. Delayed onset muscle soreness, acutely, this is not delayed. So acutely, some immediate soreness may occur because of lactic acid buildup, or metabolic byproducts, lactic acid being one of them, but that should go away in a few minutes. You may also see some acute swelling, so fluid retention, but again, that should go away in a few minutes to a couple of hours. So now delayed onset muscle soreness is not associated with lactic acid buildup whatsoever. It's completely related to intramuscular damage. So DOMS is intramuscular damage. That's related to everything we talked about before. So sarcomere damage and myosatellite cell repair. So it occurs 1 to 2 days after a strenuous exercise. So think about a time when you lifted weights and you were sore for a couple days afterwards, that you were experiencing DOMS. It can last several days. There's been times where I've had delayed onset muscle soreness for 2 weeks. It was in response to a training, a certification that I earned, and we did a lot of weightlifting in a little bit of time over a weekend, and I was sore for weeks. Same thing after a marathon that I ran. I was sore for a couple weeks as well. My quads were, and it's more likely to occur after eccentric contractions because again, you can generate more force with eccentric muscle contractions, and because of that, you create more damage. Now, this is not the same thing as overtraining. Overtraining is basically, here's another example of periodization. And if periodization occurs, but you then peak before you're completing your program, or before you hit major competition, you can lead to injury. So overtraining is excessive training, and often those results can occur because of increasing exercise intensity and volume too quickly without giving time for your body to adapt. So think about somebody that wants to run a marathon and just starts training maybe a couple weeks before, and they start running 10, 15, 20 miles to get ready. Their body's not going to have time to adapt to that. Usually when you start training for races like that, or when you start training for anything, you start at a really low intensity, moderate weight, and you build up over time. And that just gives your body time to adapt. It gives your muscle time to hypertrophy. It gives your tendons time to grow and develop and withstand that new increase in muscle mass. Or not allowing adequate time to recover. So if you're not sleeping enough, and if you're not eating properly and not recovering in between training sessions, you can overuse the muscle that you're using, and that will just lead to injury. If you're not giving your muscle enough time to recover, think the days that you are experiencing delayed onset muscle soreness, you shouldn't be lifting using those same muscles. So if you do a lower body workout and your quads and hamstrings are really sore for 2 days, during those 2 days, you really shouldn't be doing another exercise training and another exercise bout until that soreness starts to go away. Now, as it goes away, you can start training again. But when you're as sore as you're going to be, you probably shouldn't be doing weightlifting until that soreness starts to subside. And that can, if you're not allowing enough time for recovery, you can prolong fatigue. You can actually get sick. You can get injured. You can see decrements in performance. And if you're injured, then you get taken out of competition. So it's really detrimental to an athlete, particularly. But basically what happens is if you overtrain and you get hurt, then you're required to rest longer, and you're required to reduce training loads over several weeks or even months. I've seen athletes not recover from an injury and get back on their field and then just get hurt even worse. So overtraining can be it can have some pretty severe consequences. And this kind of figure in this slide tells you that if you don't use it, what happens? So reversibility is something that of course happens. Basically, if you don't continue to lose and hypertrophy has occurred, you'll start to atrophy. Your body's not going to maintain muscle mass if it doesn't need it. So if you don't continue to exercise and you don't continue to strength train, then over time, muscle cells will atrophy. So detraining occurs. It's a reversal of adaptations, and it happens so much faster. Happens much faster than time to gain. So once a certain fitness level is achieved. So if you're happy where you're at and you've gained, you can actually back off from your training regimen a bit and maintain the gains that you have accomplished. But if you stop training altogether, within days, you can start to lose what you've gained. I think in a matter of weeks, you can lose what you've gained in months. I know, sad. And I guess that's where we're finishing up. So yeah, reversibility and atrophy are two terms that you should have kind of committed to memory, and understand that training adaptations, that all of what we talked about, last as long as you demand them to. So when you stop training, the adaptations and the benefits of training go away. So again, come to class on Monday with any questions, get a chance to. I will send you guys this in an email. I'm going to save this now, and I'm going to end my session. I think that's the one. So I'm going to stop recording, and I will see you guys. I'll see you soon.